Welcome back guys again in this tutorial. Today I will show you one of the most important circuit in our daily life, that is RLC circuit. In previous video I will show you transient analysis of RL and RC circuit. Today is RLC circuit. So come to schematic and you have to draw this. Don't set the value of how in RLC circuit the graph of current and voltage is depend on the value of resistance, inductance and capacitance. So you have to calculate what is the value of this R, L and C. According to this the graph will be changed. Now first of all I must say I forget in previous video of RL and RC circuit that our voltage source is excitation is 10 volt DC. So that is called step response of RLC circuit, and previously step response of RL and RC circuit I will show you. I already show you in previous video. Now so this is step response, but if it is pulse means a square wave, then it is called pulse response of RLC circuit. But if it is sinusoidal voltage, then called sinusoidal response of RLC circuit. That is we find in transient condition in pspice. Now the graph, how can you calculate the equation of current in this circuit? So that is the theory part. I will give brief discussion, describe this. Now you can see this is the method of finding current. Here using KVL you can see. I think you study in theoretical part, and this is our equation for series RLC circuit. Similarly you can also for parallel RLC circuit. This is for parallel RLC circuit. Remember that we connect here R, L and C in series, so that's why it is called series RLC circuit. Sorry. Now here and then you RLC, and how parallel RLC circuit is connected I will show you here. And this in this way parallel is also connected, R, L and C in parallel. In this video I will show you series. All thing is same. You have to do parallel circuit. If you have any problem then you can save me. So for a series RLC circuit you can see a equation, that is second order equation of voltage. Similarly for current also, here it is for current. Now solving this second order equation we get our roots. This is for parallel, this is for series. We get a root, and this R by 2L is called alpha. Here you can see we denote a alpha for a series and 1 by 2 RC for a parallel. And omega naught is 1 by root over LC. What is alpha? Nipper frequency is called, and omega naught is called resonant radiant frequency. So here the graph nature is depend on this condition. If alpha is equal to omega naught, the graph is critically damped, and if omega naught is greater than alpha, under damped. Alpha is greater than omega naught, then over damped. These three condition of graph will. Omega naught will be same for series and for parallel, but only change is alpha. For parallel 1 by 2 RC, or for series R is equal to 2 by L. So what and how graph will come? Graph will come like that. Real distinct means when critically damped the roots condition is real equal. When overdamped, real distinct, and underdamped the roots are complex. Here roots are equal and here roots are real but difference. One roots each differ from other. That's and this you can see a graph of critically damped, overdamped, underdamped. So we wish to come this graph after our simulation. Now go to here. So in now we have to choose the value of resistance, inductance and capacitance. So this condition will give you the value of in all resistance, inductance and capacitance. When alpha is equal to omega naught means R by 2L is equal to 1 by root over LC. You get a one equation that is for critical damped means alpha omega naught. So in that equation we will set two things is constant. R1 is 10 ohm and inductance is 100 millihenry. We constant this value. So if I constant that, so R by 2L it is constant means alpha is constant, so omega naught, and L also we know from this equation we get C, value of C, that is equal to 4 amp. Means I want to say if you resistance is equal to 10 ohm, inductance is equal to 100, sorry, that means if you set R is equal to 10 ohm, L is equal to 100 millihenry, then this is you get equation 1, that is alpha is equal to omega naught means R by 2L is equal to 1 by root over LC. You get a equation, put this value R is equal to 10 and L is equal to 100, you get a capacitor value, that is capacitor value is C is equal to 4 microfarad. If you put that microfarad, not mega, remember. So in this way you can find, and this is fixed R and L. So for in case of underdamped, you get a you have to put capacitance greater than 4 mH, and for overdamped capacitance less than 4 mH, because we get capacitance 4 mF microfarad, I H called, sorry, mF when alpha is equal to omega naught, then we get a capacitance 4 mF, but for underdamped you can see capacitance greater than 4 m, and for overdamped this is less than capacitance 4. So according to this way we can set our value. So here you can see we set resistance is equal to 10 ohm, 100 millihenry, inductance and capacitance we have to set for critical, overdamped 4 when equal, omega naught and alpha is equal. So okay, now go to pspice, new simulation profile, and anything create. Now here simulation setting, and how you can run to time, from how much time to run. So this is the check and trial method you can see in RLC circuit. In RL and RC circuit we have a time constant, so we put that, but here, so how can you set this value? I show you here. If I not much small in RLC circuit, so if I put 8 second, here you can see 8 second. Okay, this is, and skip the initial condition, don't forget to uncheck that. Now we set 8 second. I don't know what is the, you can set anything. 8 second I set. Now simply run pspice. Now you're running. We forget to level marker. I forget to this, so you have to, sorry, this is we not a voltage, we have current, so set the current marker to the resistance. This is series, so all current are same, don't matter where you place the marker. And here you can see this, you can see that after means 0.5, you can say all graph are same, so we don't want to see this. Our graph is differed here, only here, so we have to make a scale larger, that is our final point. If 0.5 second, then we see graph clearly. So in that way you have to choose the value of last print step. So here's edit simulation profile, and we runtime is simply 0.5. Now simulate run. And here you can clearly get our graph, and we can see easily graph. In this way you can set the value. So this is the condition of critical damped. You can see a graph here, dome, critical, and now our next thing is under damped. Not under damped, first of all you can see anything in any order. We go to over damped. So what is the condition of over damped? Check here. Over damped when alpha greater than omega naught, means capacitance value is, what capacitance value is less than 4 m. That is for over damped. And for under damped, first of all you have to see under damped omega naught greater than c. C means greater than 4 m. So here come greater than 4 m, means I supposed to I have set a value like 10, and now save and done. Now you can see we get a curve of what? From here you can see that is over damped. And now next thing, under damped. You can see in over damped the dome is same, the last point is same for all the dome is below the this critical depth. So our you can dome is slightly below the this because we get our overdamped above this dome. Now next thing, if I set 1m means less than 4, and what is our condition? Less 4. Here you can see this type of curve means critical underdamped. This type of graph will come. Now simply cross this, minimize this and simply run. Here you can see this graph will come. You can see this is match with this, so this is the condition of underdamped. We choose value. This graph is not match like the ideal case drawn in theory, because we choose the value from ourselves. So but nearly you can say that we get a condition of that. So that's it guys. Thank you for watching and keep subscribe. Don't forget to subscribe this channel, I say must. And if you have, main thing is that if you have any problem, comment below, I will solve your problem.